All right, good evening. Welcome to the review. Exam 2 review. In a minute, I'm going to see if you have questions about general topics. We'll cover those. I'll write them down under the respective chapter. We'll cover them as many as I have time for about an hour. Then I want to save specific questions, if you have questions about practice exams or whatever, for the second part. If we don't get to your question, remember TAs have office hours, Monday, Tuesday, well, Tuesday, Wednesday, Monday's a holiday, and then I have office hours after class on Tuesday. Our exam covers the last part of the reader chapter 5, the textbooks I think is chapter 4, which is titrations. Gases, reader chapter 6, all of it. Textbook chapter 5, all. Electrons, reader chapter 7, textbook chapter 12, up to electron configurations. Okay? Folks in here from other classes, not mine? Yes? What class? Gulakar, other Gulakar folks here? You haven't had your exam yet, I guess assume, or you're really into this? How far does your exam go up to? Or totally unknown? Similar-ish, okay? So Badakis folks here? Yeah, do you know how far your exam goes to? Okay, we'll see, hopefully there's overlap. And then, or Choa, none of his folks. All right, I think that's all the instructors. Okay, I've given you time to think about what you want me to cover. Here we go, let's do it. Raise your hand if you have a topic you'd like me to cover. Yes? The uncertainty principle, for sure. That's over here. Okay, hold up. Let's see. I know you're excited now. I'll put Q, quantum. Number, okay, yes. The concept? So the two-dimensional wave function, well, particle in a box. Okay. 2D. Okay, yes. The d orbitals. Okay, yes. STP, that's over here. Yes. Way in the back. The real gas equation of state, which is the van der Waals equation. Yes?
Drawing orbitals.
Okay. Well, d orbitals and others. Drawing. I'll just do all of them. Yes. The kinetic theory of gases. An overview? Or, okay. Definitely, I think is what I heard. Nice, yes. Titrations, check. Okay. Yes, English, go ahead.
Effusion.
Confusion?
Effusion.
Effusion, okay. I cannot help confusion, sorry. Nice. Is that it? That's good for me. Oh, yes. Oh, what's the deal here? Oh, okay, okay. The ideal gas law when density is involved. Okay, I don't know why people are moaning. It could be a test question for sure. Yeah. The Rydberg equation? Yeah, that's over here. Okay, there's two of you there. One of you go first. Oh, okay, Dalton, there's a certain type of Dalton's problem that's called over water, collected over water. There was another person there, yes. Electron configure with the f orbitals, I'll do some examples next time, but I rarely ask you to write out something from the f orbitals. It could be the reverse. I give you a configuration, and then you have to figure out what element it is. I'll do one of those in class too. So I'll save that one for class, if that's okay. Yes. Balmer? Okay, I'll put that /Balmer. Okay, just a couple more. This is getting like way too much here. Yes. Change in energy is related to frequency. Okay. Change in energy. Front row? Yeah, I got that right there. Okay, last one, yes. The electron configuration, my class, we didn't get to the exceptions, so that would be final exam material. Yeah, you're welcome. Okay. All right, let's do this. Titrations are easy to do first, so let's try that. Check titrations, and if everything goes well technologically and it records, hopefully by Tuesday afternoon I can get this up. Okay, what's the deal with titrations? You're going to have a reaction for sure, and there's going to be stoichiometry for sure. Stoichiometry can really only be done with a reaction. A plus B goes to products. We're only going to care about the reactants. So you'll notice in the question, it only asks you about the reactants. You probably will be able to, or need to write the reaction yourself. That's not uncommon. So let's say it was nitric acid, so you'd write this, reacts with strontium hydroxide. That'd be this. Okay, so you need to write the reaction. It's a double replacement or neutralization reaction. Strontium goes with the nitrate. Strontium is 2 plus, nitrate is -1, so you need 2 of them, and then 2 waters, and I think to balance it, I'm going to put a 2 there. So you won't care about the products, but you only need them to balance the reaction. Once the reaction is balanced, you won't care about the products anymore. So they could say, for example, say this is 0.1 molar, and say there's 10 milliliters of it, and we want to know the molarity of this one, given that there's 25 milliliters. Okay, so that'd be a pretty typical question. One is known, and the other is unknown, but I could know a little bit about it, but there's still something else I want to know about it. What you're going to do is your typical stoichiometry. Step 1, go to moles. Step 2, molar ratio. Step 3, go to the requested unit. Remember that molarity is moles per liter. So I'm going to start with what's known. That's the nitric acid. I'm going to say, well, it's 0.100 moles per liter. That's of the nitric acid. I'm going to get rid of the liter by multiplying by the volume, but I will need to do a little conversion here because there's 1,000 milliliters per liter. So you notice the liters and milliliters cancel out. Now I have moles of the nitric acid. Now I need to do a molar ratio to get to the place where I'm asked about, which is the strontium. There is 1 mole of strontium hydroxide for every 2 moles of HNO3. Okay, so now the moles of HNO3 cancel out, and I have moles now of the strontium hydroxide. Okay, remember I want moles per liter. I've got moles, I'm halfway there. I just need the volume, which is here on the bottom. So I'll do this in a different color. I basically need to take the moles and to divide all of that by the 25 milliliters. However, the 25 milliliters is in the wrong unit. I need it in liters. So I'm going to say, well, there's 1 liter per 1,000 milliliters. The milliliters will cancel, and I'll be left with liters in the denominator, and that's what I want. I just made up the question, so I don't know what the numerical answer is. You can do that at home with your friends. Okay? Any questions on this before I go to the next thing? I'm going to try to go a little bit fast so we get through as much as possible. All right? Well, I'll kind of leave that up there. We'll go to gases now. STP, that'll be a quick one. Okay, gases, STP. Other classes, I don't know how your instructor clarifies this, but STP, standard temperature, this is not the confusing part for most students. That's 273 Kelvin. That's the temperature. The pressure is what confuses most people. Technically, standard pressure is 1 bar, not 1 atmosphere. So when you see this, and this is a new thing, this is the last several years, so some instructors might not be up to date, but it's 22.7 liters per mole if you need to use a conversion. So if you're at STP, you can use this conversion right here in stoichiometry or any sort of conversion that's necessary. That's all that STP means. Okay? Any questions about that? There is a 22.4 liters per mole. That's not STP, technically. That's 1 atmosphere at 273 Kelvin. So if you see STP, know that it means this. And if you need, the conversion is this. Yes? Yeah, if you have a PV equals nRT is the question, what do you do with it? Because R is 0.08206 liters atmospheres per mole Kelvin. That's fine. You don't need to worry about R at all. T, you would plug in 273 Kelvin. P, you would plug in 1 bar, technically for my class, that's standard pressure, and you can convert to atmospheres using the back of the test, 1.01325 bar per every 1 atmosphere. That would be on the back of the exam, that conversion. If you do that, notice what's left. You have a V and an N. So you'll calculate this ratio. So using the ideal gas law or this ratio is the identical thing. Any other questions on this? Or we'll just bust through the gas law chapter first. Okay, next, let's do the real gas equation of state. Okay, and I want to show you something. So for real gases, there's 2 parts, 2 areas you want to be familiar with. One is the concept and the other is the calculation. Okay. So the concept is that the 5 assumptions of the kinetic theory of gases, so this will connect to kinetic theory a little bit, that's nice. Kind of be doing both of those at the same time. The kinetic theory of gases has 5 assumptions. Those 5 assumptions are things like gases take up no volume, elastic collisions, temperatures proportional to kinetic energy, the atoms, particles move in straight lines, random kind of directions, that sort of thing. So there's 5 assumptions. You should know those 5 assumptions for the kinetic theory of gases. You don't need to know the derivation. For a real gas, those one or all of those 5, one or some combination of those 5 assumptions break down. So I talked about a breakdown of some of those 5 assumptions. And that's what's in the bullets in the middle of this page in the reader. This page of the reader is page 54. Okay. So, for example, let's see, what's a nice one to do? The bottom bullet. The molecules take up volume in the container. That volume is not negligible, so you have to do a volume correction. And so that breaks down the assumption that molecules take up no volume, or gases take up no volume. So that's the bottom bullet. Yes?
So are these just some of the breakdowns, not all of them?
This here has, I go through some of the breakdowns of the ideal gas law, or kinetic theory of gases, really. Yeah. So that's what's in the bullet. So if you want to know the breakdown, that's the bullets part. Okay? I go through a couple others. Kind of another big general area is that for ideal gases, usually we're working at low pressure and high temperature. Low pressure means around atmospheric pressure. High temperature means around room temperature. As the temperature goes down or the pressure goes up, those assumptions break down again, and that's what the first bullet is about. So as the pressure goes up, there's more interactions and the gas becomes more real or less ideal. Or as the temperature goes down, they go slower, there's more interactions. the assumption that there's no interactions breaks down again. So that's what the top bullet is really about, kind of different categories where that can happen. So just be familiar with those sort of things on a conceptual basis. There's two calculations in this little section. The one is the top equation right here. It's just the ideal gas law kind of reconfigured and solve for 1. If I ask you on a multiple choice question, I give you the pressure, volume, moles, and temperature, and I ask you, is this a real gas or an ideal gas? You would calculate that, PV divided by nRT, and you see if you get the number 1 or a number really close to 1. If you get a number really close to 1, that's called the compressibility factor. It's an ideal gas. The further the number is from the number 1, the more real it is. Okay, so the number 1 is a way to measure, is this really ideal or not? Okay, so that's one calculation. The second one is what's on the very bottom of the page, same page, here. This is called the van der Waals equation of state, or the real gas equation of state. And the only way this can possibly be in a math problem is if I literally give you the two constants in the equation, A and B. A and B are specific to a particular gas, so there's no way you could memorize it. It's just something you would look up, or on a test I would give you A and B, those two variables that you see. And this would be the same for other instructors too. Those two, A and B right there. They would have to be given. To make the math a little bit simpler, you'll see if you see this on past practice exams, we're going to ask you to solve for the temperature. That's kind of the easiest thing to solve for in this, because it's the only one on the right-hand side by itself. Solving for volume or something like that would be a little too crazy for this equation. So it would be a plug and chug, there would just be a lot of variables. Okay, any questions about real gases? So know the concepts, that's the middle of the page that you would want to be familiar with. And then there's the two equations. The one at the top to find if it's equal to 1 or not, that tells you if it's how ideal it is. And then the one at the bottom. I'd say on practice tests you see this more rarely. Probably in the last 10 years it's been 2 times or so. Okay. All right, that's the real gases. That kind of connects to the other topic that was just asked about, which is kind of a nice connection, the kinetic theory of gases. I would say this, and this is probably true for the other instructors, I'm not totally sure. Here's what you would need to know. 1, the 5 assumptions, so note that down. Read over the 5 assumptions, you just want to know them conceptually. And then you want to know the kinetic theory of gases. What it basically does is derives the ideal gas law. So using kinetic theory of gases, you can derive the ideal gas law from first principles. That's kind of the interesting thing about it. There are a couple of equations that go along with it, and one more concept. Okay, so you wouldn't need, for my class, definitely not need to know the derivation. The equations that come out of it are the ideal gas law, and 2 kinetic energy equations. These will be listed on the back of the exam, so you don't need to memorize them. That's really what comes out of it. Oh, and then one more, there's the root mean square velocity. These are, definitely all the ones at the bottom are very plug and chug. There's not really tricky ways to word the problem. It's just as it is. You plug it in. You just need to make sure to do the calculation correctly. The capital M in the root mean square is what?
Molar mass.
Molar mass, and it has to be in what units? Kilograms per mole. Those are the most common mistakes that 1/3 of you or more will make, or probably the students who are not here. Okay? So those are really common calculation problems that you pretty much see on every test in one way or another. Okay, there's a couple concepts that come out of here. Oh, yes. The EK there is the kinetic energy. The question is, where's the kinetic energy? And really you're calculating, the question is it the average kinetic energy? Yeah, that's pretty much what you're calculating. The average, and it's the kinetic energy per mole. That's what the little hat or squiggly on top of the kinetic energy means. So you find the kinetic energy per mole, or really the average kinetic energy per mole. Okay, A couple concepts that, oh yes. Great, which R are we plugging in? The 8.3145, because you have to be consistent with the units. If you're a little fuzzy on that, the page 61 of my reader summarizes the unit issue table right here in the middle. How do you know which gas law constant to use? Basically, you'll only use the top one if it's ideal gas law. Okay. Now the concepts. Okay, based on the kinetic energy part, at a given temperature, all gases will have the same average kinetic energy. That's one concept. And because that is true in the other kinetic energy equation, the heavier something is, the slower it goes, and vice versa. The lighter something is, the faster it goes. So those are the concepts. Heavier goes slower, lighter goes faster, and if things are at the same temperature, they have the same average kinetic energy. Those are the concepts that come out of really these equations right there. Okay? So know those concepts and how to do this math. You'll see some sort of conceptual question from kinetic energy somewhere on the test for sure. That's pretty normal. Okay. Did I miss anything on kinetic energy that you're curious about? Not kinetic theory. Kinetic theory is derived for ideal type gases. Okay, I'm going to go back to this. Let's do this PV equals nRT when density is around. We just talked about PV equals nRT. Okay, when you have an ideal gas law problem, there's a couple things to remember. PV equals nRT. You know you're going to use this if you see the variables used, like pressure, you see a temperature, moles, things like that. And if the states are not changing, that means temperature is not changing, pressure is not changing, etc. If things are constant, it's probably going to be this. Okay? Now this can be paired with two other equations. This will be given to you on the test, though most of you probably have memorized it. These equations I usually don't give, or other instructors don't give. This one and this one. So the molar mass is equal to the mass of the moles. Make sense, it's grams per mole. And then the density is mass over volume. These all can be paired together in a combination, or it's called a variation of the ideal gas law. So how would that work? If you're given if you have the density in a question, this is one possible calculation question. So if you see density, right now for this chapter, the only possible questions are, it's a variation on the ideal gas law, or, I had just thought of another one that involves density. If it's a pressure equals density times gravity times height. But that one's for liquids. So if you have a liquid and it's pressure, it's that one, and density. If you have a gas and density, it's this one. So, but that's, in these chapters, I think that's the only two times you'll see density. You've seen it in other chapters, but not for exam 2. So anyways, what would you do if you had a combination of these? Either you can use the equations all separately. So like, I'll use this to find the volume, and I'll plug the volume in here. Or you can combine them, and sometimes it's required to do so because there's variables missing. So if you need to combine them, it's just going to be algebra. For example, I see volume here and volume there, so if I solve for volume here, volume is mass over density, I can put this with this and go pressure, mass over density equals nRT. That's one way I can do a little substitution. I could also say, kind of write this out a little bit, P over M is D, nRT. I could also substitute this equation in, so I could say, let's go a different color here. Mass is moles times molar mass. If I solve for mass there, and then I can plug that in mix these two equations. So I could say pressure times moles times molar mass over density is nRT. So now I have all the equations all together. It really depends on what you're asked. So if I put this all together, that's P times molar mass, not molarity, is density RT. This is not necessarily the equation, it's just a way to put things together. So if you see density and molar mass, this version of the equation is the most helpful. But you've kind of got to mess around with what's written in black here and rearrange them based on the variables given. Again, if you see density, molar mass, and pressure type variables, pressure, volume, temperature, it's probably a combo problem that uses a combination of these three equations written in black. Okay, so that's called a variation on the ideal gas law. Any questions on that? Okay, so this is just plug and chug. The hard part for most students is how do I manipulate these to get the equation I want, which is unfortunately just algebra. Okay, next we're rolling. A fusion. A fusion, what the heck is that action? That's when you have some sort of container with a hole in it, and in the container is a gas, and the gas escapes out of the hole, or the orifice, and when that happens, that's called a fusion. So a fusion is escape of a gas out of an orifice. As opposed to diffusion with a D, that's if you just release a gas and it migrates randomly throughout a space. That's diffusion. So they're slightly differently. A fusion is technically connected to, so this is a fusion. This is technically connected to Graham's law. Though diffusion will work as well. So if it's diffusion or fusion, most of the instructors in 2A don't care if you use Graham's law. Though technically, just so you know, it's with a fusion. Should I say something about Graham's law or no? Yes. Okay. What the heck was Graham's law? And when do I use it? Okay, so it's pretty easy if you can just get it straight in your mind to know when to use Graham's law. First, what is it? I like to write it this way. The molar mass of gas A over the molar mass of gas B equals, so this is the key thing here. This can equal 3 or 4, I have to remember, different things. This could equal the velocity or rate, usually the root means square velocity, of B over A. So notice A and B are inversed here. So this is the style of the equation we'll give you on the exam, though this, it's not just rates it's equal to, yeah?
Is the square root over the MA over MB the whole thing?
Oh, the whole action.
Okay.
That's right. Is it over the MA and the MB? Yes, all of y'all. Okay. It can also be D distance of B over distance of A. That's distance that the gas travels. That thing on the left could also be amount of B. So the moles, for example, over the amount of A. Oh, it's capital A. Or it could be time. Time is the only one that's not inverse, so T of A over T of B. So these are really 4 versions of Graham's law. We typically, as instructors, only give you the top version, and you just have to know that the 3 other versions are in play. It's pretty easy to know which, if it's a Graham's law question, and that's if you're comparing 2 gases. And you want to know something about rate, distance, amount, or time. So that's how you know if it's a Graham's law question. So for example, I'll get your question in just a second. If we ask you about rates, and we say we want a ratio, or we're talking about 2 gases, it's Graham's law. If we're talking only about 1 gas, and we want to know about rate, then you're going to use this equation. So if it's only 1 gas, it's this one. But if it's 2 gases, it's going to be a version of this. Okay? The other thing I wanted to mention, what units should this be in? So you might be led to kilograms per mole, and that's fine if you do that. It doesn't matter, though. Why is that? Because it's dimension, it's a ratio. So whenever there's a ratio, if it's Graham's law, Boyle's law, Charles' law, those kind of ratio laws, it doesn't matter the units as long as you're consistent. So as long as both of these have the same units, you're fine. Same as all of these. As long as they're the same units with each other, you're fine. You have a question? Are all four under the square root? Well, this side doesn't change. So this always has a square root. And these do not have a square root. They're just ratios. Okay. Any questions about Graham's law? Okay. You recognize it because there's more than one gas, and it's asked you about one of these variables. Okay. Dalton's law is going to take us a little bit more time, but I think we can kind of move through it. Dalton would specifically over water. It's a certain style of Graham's law that you'll see pop up here and there. I want to point to the page in the reader that you see it. It's on page 60. Let me say some stuff about it. Okay. If you're going to see the phrase collected over water, or some variant of that. That's the key phrase that it's this kind of question. It must use a phrase like this in order to exist. So if you see this phrase, it's this kind of question. There's nowhere else that you're going to see collected over something. All right, not in Chem 2. So how does this work? The experimental apparatus is you have some sort of reaction, and out of the reaction comes a tube, kind of like that. And that tube goes into a container, like a beaker or something like that, and that container has water. Okay, so a gas is coming off of the reaction. So a gas is a product of the reaction, and it goes out the hose or out the tube. If the tube was just here, it would bubble because it's underwater. And there's a certain setup. You're going to do this in the last lab of the quarter, the Avogadro's number lab, where you take some sort of collection device, usually a graduated cylinder, and you put it upside down. So this is a graduated cylinder, usually, or a burette or something like that, and it's upside down, and the gas bubbles into here, and you measure the volume. So that's experimental apparatus. This helps us, this experiment helps us do basically stoichiometry calculations. Okay, you don't necessarily need to know what it looks like to do the calculation though. So this sort of calculation has two steps. These steps can be done in either order depending on what's given. Step one, again, it's not really in order, you can do them in either order, is that P total, and I'll explain this in a second, equals P gas plus P water. Okay, that's the first kind of step. So, in this upside down brown cylinder, graduated cylinder there's two gases. The gas that's coming off the reaction, and we call that P gas. That's what P gas is about. You see P water, where do you think the water is coming from? The water. It's the vapor pressure of the water. So the water is a liquid and it's vaporizing. Okay? So there's two gases in there, water and the gas from the reaction. We care about the gas from the reaction. P total is just atmospheric pressure. So this is from the atmosphere. If it's not given, then you use the units of atmosphere. So for example, this would be, in atmosphere is 1 atm. Or in millimeters of mercury, 760. What are other units? Torr, 760 torr as well. Etc. It's the atmospheric unit. So if they don't give you that number, you just use atmospheric pressure. Okay? P gas, this is usually what you want to know about. You're trying to find the pressure of the gas to do some calculations of whatever. This one here is found from a table. Like, what the heck? A table? Yes. You just look it up and you plug it in. And that table is given in the bottom of the page 60 of the reader. It's also in the text. You just find the temperature, and this is literally the vapor pressure of the water in millimeters of mercury. You might think, how the heck would we know that on the test? Well, and other instructors would have to do this too. Do you have to memorize it? No, I give you that table. It's on the back of the test. It will look like this, right there. So, if it's ever a Dalton's collected over water problem, you'll probably have to use this table. We'll give you the temperature, and you just take the vapor pressure of the water. here. So you literally take this number and put it into this equation, whatever the temperature is. So it's a plug-in. I've also, for fun, had really funny multiple choice questions where I said, the temperature is 25 C. What is the vapor pressure of water? And people are doing all kinds of crazy calculations. And all you need to do is look up that number right there. That's the answer. Okay? So there's no craziness. It's literally, if you need the vapor pressure of water at certain temperatures, from this table. Okay? This will be on the back of the exam. If you're in my class, in my practice exam reader, you have literally what's on the back of the exam on the first couple pages of that reader. Okay? All right. Step 2, again, really can be any order, so it depends where you start with. Just pressure the gas. Okay. And sometimes, depending on what you're asked for, you only need one of these, but you won't need more than these equations. The moles of the gas is from the ideal gas law. Pressure of the gas, volume over RT. So it's just the ideal gas law. Sometimes we'll give you this data and we'll say, hey, what's the moles of the gas? So what you would do is you put atmospheric pressure here, or whatever pressure is given. You get this from the table and find P of the gas. And then this number goes right there. You got V, you'll have R and T, you find the moles of the gas. It could be the reverse. We give you the moles of the gas, you find the pressure of the gas, and you go up this way. So this can go either way. This equation could be used first than this one, or they can be used separately, meaning it could just be this equation or just this equation, for example. So that's the Dalton's collected over law. You're using like a form of Dalton's law in this when a question is about being collected over water. All right, you'll see a question like this, maybe not every year on exam, but every couple of years, every other year, or something like that. We'll have a collected over water question. Okay. Questions about this? Okay, thinking, or whatever you're doing. That's all the gas law questions. We're making good time. We need to move over to electrons.